Let me open this segment with two questions which I want you to answer. Is water compressible? Is the Earth flat? Some engineers find the change from thinking about hydraulic systems only in steady state terms to thinking about transient hydraulic behaviour as difficult as our ancestors had in making the leap from the notion that the Earth is flat to believing it is a sphere spinning in space. In this segment, we will look at the way that WATHAM and the method of characteristics look at finite water sections. I want to help you think about the physics of transient hydraulics at a micro level compared to the macro steady state hydraulics level. Engineering experience and training allows us to think about tanks, valves, pumps and pipes in terms of a macro view. For example, pump flow rate. Is the pump on or off? Tank water volume. Is it filling or emptying? Is the valve open or shut? That level of understanding is only appropriate for tanks, valves and pumps in transient analysis. For transient analysis of pipes, we need to understand a more microscopic view. We need to look at water sections within pipes. Considering a system made up of multiple pipes, each pipe will typically have a different length, and the compressive wave speed, also known as the celerity, is likely to vary from pipe to pipe based on the pipe's material, diameter and wall thickness. Here we are looking at a diagram of a simplistic system of 3 pipes. The water in each pipe has been divided into a number of water sections. What do you notice about the way these pipes have been divided into water sections? It's important to note that each pipe is divided into a whole number of sections. In addition, the length of water sections can vary from pipe to pipe. The method of characteristics is probably the most effective of the mathematical techniques used for solving transient analysis in pipe networks. In comparison to some other methods, it can report on the conditions in pipes in between junctions and nodes in the model. It enables a very complicated set of equations to be solved as long as 3 conditions are true. The same calculation time step is applied to every pipe in the system. All pipes are divided into a whole number of sections, and during one time step, the compressive wave travels exactly 1 water section in each pipe. Achieving these 3 constraints exactly in a system with multiple pipes is relatively difficult without making some form of compromise. To satisfy these 3 rules exactly in a system of multiple pipes, WATHAM adopts the option of adjusting the compressive wave speed or celerity used in individual pipes. Some other transient analysis software packages choose to adjust pipe lengths instead. WATHAM adopts its choice on the basis that celerity input by the user is likely to be an approximation, known with less accuracy than data such as pipe length and junction location. Let me give you a stronger understanding of what this all means by looking at an example. This table shows the input pipe data for the WATHAM model of a groundwater bore field. Some pipes in the system are relatively long, being pipes connecting bores together. In this case, the bore collector mains are medium density polyethylene. As a result, these longer pipes have a relatively slow celerity. Other pipes in the system are very short. For example, the riser pipe down each bore and the horizontal wellhead piping. In this case, the short pipes are mild steel and as a result have a relatively fast celerity. This table shows how WATHAM responds to a user applying a 0.1 second calculation time step to all pipes in this bore field. Start by looking at the column labelled sections. It records the whole number of water sections, Note that WATHAM can easily calculate a whole number of sections for the longer pipes. Note that each short pipe with length less than 40 metres has just one section, which highlights one of the constraining rules for the method of characteristics. In these very short pipes, during 0.1 seconds, the compressive wave would travel far beyond the length of the pipe at the correct celerity. Now look at the column labelled celerity. It shows the wave speed that WATHAM will adopt to achieve exactly an even number of water sections in that pipe. Then the final column shows the percentage adjustment that WATHAM applied to the celerity compared to the user's input celerity. Note long pipes mostly have very small adjustments. Cases highlighted in red indicate totally inaccurate, unacceptable adjustments. The red in this case indicates that a 0.1 second time step is inappropriate for this model. So let's take a look at how WATHAM would respond using a calculation time step of 0.01 seconds. We still have some short pipes with only a single section in the sections column. In the percentage celerity adjustment column, we can see that the celerity that WATHAM will use for the longer pipes is very close to the celerity specified by the user. The shortest pipes, 5 metres long, remain highlighted in red because their celerity adjustment is greater than 25%. WATHAM treats these as fatal errors and will not allow a transient simulation to run with this level of inaccuracy. Bore riser pipes, 28 metres long, have their celerity adjustment highlighted in orange because the adjustment is less than 25% and more than 10%. WATHAM treats these cases with a warning message. WATHAM leaves it to the user's discretion to accept or reject this level of inaccuracy. Now looking at the consequences of using a calculation time step of 1,000th of a second. With this very small calculation time step, we can see that all pipes will have a whole number of water sections and acceptable adjustment of celerity values. The largest celerity adjustment is 3.5%, and most values are very close to the input celerity. With very fast and powerful computers available in engineering offices, the most practical approach to achieving the required level of accuracy is to use a sufficiently small calculation time step. In some water system models, users may be able to delete very short pipes without compromising the overall validity of the water system model. For example, it is common to omit the suction and delivery pipes in a pump station and represent these assets just as nodes on each side of the pump. Summarizing the messages about the method of characteristics and water sections. Recognize that the user manually defines the time step that will be used. In this way, you retain control over the level of accuracy applied to the model. WATHAM divides all the pipes and calculates the required number of whole water sections. WATHAM appropriately adjusts the pipe celerity used. WATHAM tells you in its log file whether your selected time step is accurate enough to allow the transient simulation to run or not. Cases with celerity adjustment less than 10% are considered sufficiently accurate. WATHAM puts a warning message in its log file for each pipe with a celerity adjustment greater than 10%. A fatal warning error will be written in the log file for pipes with celerity adjustment greater than 25%. And in these situations, WATHAM will not run a transient simulation. Now that we understand how WATHAM calculates the number of water sections in each pipe, let's take a closer look at an individual water section. From our steady state ideas about hydraulics, we may start by thinking that all sections in one pipe flow at a uniform flow rate throughout the entire pipe length. While this is true during steady state conditions, it is not true during transient events. Here we are looking at a single water element in one pipe. I want you to think about this water element as though it was your car travelling along a single lane section of the freeway. Your car is surrounded front and back by lots of other cars. It is bumper to bumper everywhere. At each time step in a transient simulation, WATHAM would evaluate the velocity of the rear bumper of your car. At the same time, WATHAM would evaluate the velocity of the front bumper of your car. This is what WATHAM is doing for every water parcel in every pipe in the model. Or in your case, every bumper on every vehicle on every street in the city. What does it mean if the rear bumper of your car is travelling faster than the front bumper of your car? That's right, your car has been compressed. What does it mean if the front bumper of your car is travelling faster than the rear bumper? That's right, your car is being stretched. This is the technique that WATHAM uses to evaluate whether the pressure within each water parcel is being increased or decreased, or staying the same compared to the last time step. It's important to understand that WATHAM operates at a single ambient water temperature. WATHAM cannot include thermodynamic effects related to changes in water temperature. At a single temperature, it is tracking at each time step the current pipe flow and adjusts the pipe friction accordingly. And of course, it tracks the operational state of all the engineering assets such as water level in tanks and pressure vessels, air inflow or outflow rate at air valves and standpipes, opening position of valves, and the current operating speed of pumps, etc. Elasticity and compressibility of each water element in the system, water section pressures, and it tests that the water is in the liquid or vapour phase at each time step, the quantity of water vapour contained in each water section, velocity changes to account for acceleration and the water momentum in the system.